upload the solutions to the homework problems. So give me 1 sec. Yeah, so there were 2 problems. One is decently hard. The other is really hard. Do you want to talk about the first one first? All right, so count cross. Whoops, no, that is not the solution. All right, so here it is. So the way I represent the map, when I was doing it, I didn't actually use the trick where I put roads in between. So I essentially multiplied the grid coordinates by a factor of 2, so that for the even coordinates, that's like the real points, and then for the odd coordinates, that's like you can use that to determine to specify whether there's a road in between those 2 points or not. There are alternative ways of representing the map, and one of it is for a 2D map. I actually make a 3D array. So the third dimension is of length 4, and it specifies like which whether there is a road to the north or to the east or to the south or to the west of that particular point. Once we're able to figure that out, the rest is just the flood fill algorithm. And again, the main thing with the flood fill algorithm is make sure that you have a Boolean array to store whether you are visiting, whether you have visited that particular point or that you are putting that in a queue. So yeah, that's my solution. Any questions on this? All right, so let's go ahead and look at the much harder one. So it's called Where's Bessie? Actually, who here has attempted it? I think one of you have. I'm going to show the solution here as well. So basically, you have a 2D map, and you have to find sections in which you have you have a certain condition within that sub area in that 2D map. You're trying to find within that sub area whether there are only 2 colors, and one color forms one region and the other color forms 2 or more regions. So what you have to do is use a quadruple loop to loop through all the different possible bounds for the left and right bounds of the rectangle and the top and bottom bounds, and then do flood fill within that bound. But the idea is essentially the same as any other flood fill problem. I'm just going to leave it here so we can look at this if you like. So we're on to the last 3 days of our class. What I'd like to do is we're going to cover one last topic. It's very similar to flood fill, called breadth first search. Or graph search, and the concept of adjacency matrix is also very related to that. So yeah, let's get started. So why don't I go ahead and pull that up first, pull up a musical problem with that first. So this one's called MooCast. All right, so here is here's the link to this problem. Yeah, so let's spend a few minutes looking at this.
Is this straight line distance or Manhattan distance?
Uh, Straight line distance.
Okay.
Not that it matters too much. It's just, yeah, concept is the same. All right, how are we doing? Good. Let's go and talk about this. So the thing that's tricky about this, the thing that's hard is right. So we need a way to store whether given any two cows, cow I can broadcast to cow J, right? Um, and so like let's say like A can talk to B and B can talk to C, C can talk to D and so forth. You want like if it's written out like this, right? It's easy to see, right? Then cow A has the longest chain, obviously, but we're looking at a structure here where uh, the arrows can go like the other way and they can form cycles. So in general, this structure is called a graph. A graph is basically points or nodes uh, that are connected by these things called edges. Okay, so with if you know what a tree is, a graph is very similar, except a graph allows uh, um, arrows to go both ways. So with a tree, the direction of the edges usually just go one way. With a graph, it's allowed to go both ways, and it's allowed to form cycles. All right, so points that are connected by edges, and in this case, um, the points here can represent the cows, right? And then the edges can be like so there's an edge pointing or an arrow pointing from cow I to cow J if cow I can broadcast to cow J. And we're trying to find the node that can reach the most neighbors. Okay, so we can run this standard algorithm called breadth first search or depth first search. That's really similar to flood fill to figure that out. Um, but first, we need a way to represent the graph, and that actually isn't too bad either. There's 200 cows, right? Um, so, and we need a way to keep track of whether any cow can reach any other cow. So we can actually use a 2D array. I'm going to call this graph. And the concept is simple. It's two indices. So graph of ij denotes whether cow I can broadcast to cow j. Yeah, once we have this representation, it's not too bad to apply the flood fill like algorithm, right? You start at a point, right, and then you go to all the neighbors that that's reachable from that point, from that node, right? And that's assuming that you haven't visited them in the past, and then you kind of recursively do that thing over and over again until you visited all the nodes uh, that can possibly be reached from the starting point. Yeah, so I'm going to go ahead and do that on the pad. Let me go ahead and create the starting code for it. So starting code, the name of the problem is called MooCast. All right, so here's the MooCast problem, and let's go and parse the input first. Okay, so n being number of lines, right, and number of cows. Okay, next, what do we got? So the next n lines, they denote the coordinate of the x and y coordinate of the cow, followed by the power of the walkie-talkie held by that cow. So a cow is defined by three numbers. We can create a cow class for that, or if we're really careful, 2D array would actually suffice as well. So a cow is defined by three numbers, and I'm just going to be really careful with the comments. So cow of I of 0 and cows of I of 1 denotes the x and y coordinate of cow I. And then the last number, cows I of 2, denotes the walkie-talkie power of cow I. Yeah. Loop n times, parse the inputs. Okay, and then what we can do next is construct that 2D Boolean array that I was talking about earlier, the 2D graph Boolean array, right? And again, the representation here is graph of I, j denotes whether cow I can broadcast to cow j. So we can populate this, and the way we do that is for each cow I and for each cow j, right? Now, one thing that the problem reminded us about is uh, the edges can be asymmetric, right? So just because cow I can talk to cow j doesn't mean cow j can talk to cow I. So when we're looping, we got to be careful. We can't just loop from like I plus 1 like this. We actually need to loop through the entirety of the indices. All right. Yeah, so there's that. And so now we figure out whether cow I can talk to cow j. All right, so we need to find the distance, and So I'm going to do int dx, so that's the difference in x. So it's equal to cows of I of 0 minus cows of j of 0, right? Difference in y, same thing. And we want to check whether they're in range or not. So we want to check whether this distance, um, since it's straight line distance, right? So we have to do like dx squared plus dy square less than equal to, what is it, the range of the walkie-talkie square, right? Range square, right? All right, so we're going to apply that formula. So plus dy times dy less than equal to, so if I actually leave this as squares, right? So like sometimes people like to write this with like a square root on one side. Uh, I like to avoid that because if you're dealing with square roots, you have to use doubles, and they are imprecise, and we can get away with not using it anyway. So let's do that. So cows of I 2 squared, right? All right. So if in range, then set that to true, right? So graph of I and j equals in range. Great. Yeah. So that's all we really need to change the representation of to have the graph representation of the cows. Questions so far? So next, what I want to do is go through the algorithm called breadth first search, and I want you to look at my screen share for this. Okay. So let's suppose you start at a node, and I'm drawing it as a circle at the top, and so that represents a cow, right? And then there's like other cows that we uh, can go to, followed by other cows that we can go to, so forth, right? So for now, I want you to imagine that these lines, their edges, and I'm not going to bother drawing arrowheads for all of them, but just assume that all these lines, they point downwards, okay? So this goes down as well. So this looks more like a tree structure, and but in reality, this could actually get a lot messier. It's possible for these edges to be, for these nodes in this second layer to be pointed to by multiple nodes in the first layer. So I'm grouping these nodes by layer, so I can call the top layer layer of level 0. This is level 1, and this is level 2. Um, and the level number kind of denotes like how many nodes, how many edges you have to hop to from the start node to get to that node in particular. Okay. Right. So the idea is we want to visit all the possible nodes that we can from the start node, right? And this is what we do. We go to the start node, okay, and then we can queue it up, uh, and we can queue it up with an actual queue, or we can do it recursively. Either way is fine. And the next step that we do is actually to queue up. What I mean by that is I queue up these neighbors, right? So this guy, this guy, this guy. Say, hey, go ahead and visit all the nodes that you can visit from these guys that I am highlighting in red. Okay, right. So we go down here, and that in turn queue up everything that it can get to, namely this guy, and this guy, right? So it's going to queue up all of them for recursive call, okay? Uh, and then when those are done, right? So I'm not going to go further. When those are done, keep in mind that these guys were actually queued up at some point, right? When we start from the beginning. So we're going to go to this guy and queue up all the nodes that it has visited that hasn't been queued up before, right? Which is this guy here. So we go visit that, right? And then the last one that we've queued up that we actually haven't visited is this guy here, and it's gonna queue up that guy, right? So that's the process that we're going to be making, and um, it's actually called depth first search. This particular process, and you can see here there's a lot of parallels between that and the flood fill algorithm.
So I think I've heard of like a different type of search as well called like breadth first
Yeah,
search.
this breadth first and depth first. For this problem, it's not necessary to go over what the difference is. And in fact, I did kind of say I want to talk about breadth first search in the beginning of class, but what I end up doing here is depth first. So depth first is easier to implement recursively. So if you're comfortable with the recursive algorithm that we've done for flood fill, that is a special variant of depth first search. So what I mean by depth is, so if I rewind this, is I go as deep as possible in this tree structure. So I start with this guy, right? And then I say, hey, I need to queue up these guys, but I'm gonna visit this first, okay? And then this guy here, it's gonna uh, queue up these guys, right? And actually, to be more clear, let me mark the guys that I've actually visited, not just queued, actually visited with a different color. Okay, so like by the time I've visited this node, like this is the state of my graph. So in red are the nodes that I've queued up, uh, and in yellow are the nodes that I've actually visited already. So nodes that are queued up are slated to be visited, but they haven't been visited yet, and we need to visit all of them to be able to find like what are the other nodes that's reachable from those nodes. Okay. So next we visit this guy, and we don't need to add additional nodes. And then we visit this guy, and we don't need to add additional nodes either. And then what do? We go back. We actually backtrack. Like this one way to think about it is we're like backtracking along this node, this edge, and then backtracking along this edge, and then going downwards again. But what the actual implementation, we don't actually like backtrack. That's really complex. Now keep in mind that these two nodes are already colored red. So what that means is it's already queued up somewhere uh, to be slated for visitation. Okay. Um, And if you just write that recursive thing that you do with flood fill that I showed you on Friday, uh, then you're already doing that. Okay, so we visit this guy and then queue up these guys, right? And then we visit this, visit that, okay, and then we visit this and queue up this guy, and then finally we visit that. So that's depth first search. If you want to know what the difference is between that and there's another one. It's called breadth first search. So uh, the thing I just showed you is called depth first because it goes like as deep as possible, like along one path, essentially, right? And then when it can't go any deeper, it kind of backtracks and then it goes as deep as again as possible. Breadth first search works a little bit differently in that it starts by visiting all nodes in level 0 and then queues these up. And then it goes to this guy, and then it's still going to queue this up, but the order in which we visit is a little bit different. We don't visit these guys that we just queued up. Instead, we visit them in the order in which they have been queued. So the next guy that we visit is actually this guy, and then we queue these up. Okay, and then this guy, and then we queue that up. Okay, and then bang, 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 bang. For this problem, it doesn't really matter which way we do it. There are other problems in which it does. Specifically, if you want to know the minimum number of edges it takes to go from a start node to another node, then you would want to use breadth first search. So breadth first search is you visit all nodes in level 0, then level 1, then level 2, and so forth. And again, for this particular problem, it really doesn't matter which one you use. But for other problems, you might need to use breadth first search, and you would need that. So need this algorithm if you want to find the uh, the 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 path length between two nodes. In other words, how many levels there are between two nodes. All right, questions on this? All right, yeah. So let's try this. Let's try to implement this guy. So our objective in creating this breadth first search or depth first search really is to count how many nodes is reachable from a starting node, right? So I'm going to do int. I'm going to create a function. It's going to return a count. Okay, and it's going to look like that. Okay. So count of graph start returns the count of number of nodes reachable from the start node. One minor difference between breadth first search and and flood fill that we did over the weekend is with flood fill, like a position is defined by like a row and call indices. Here it's defined by just one index. So the start node, we identified it by one index, and that's a number from between 0 to n minus 1, right? Before I go on, has anybody heard of what a queue is in Java or in other languages?
It's like the first element that you put in has to also be the first element that you take out, right?
Yeah. Um, who has not done anything with queues before?
I just know what they are.
I haven't. Yeah, I haven't done anything with it, but I kind of
Okay.
know what it is.
All right. In that case, how about yeah, it's really not that difficult. It's just you can almost think of it as an array. It's certainly like a linear data structure, like an array, where you can add stuff to it, and you can say add or remove. So when you add stuff to it, it adds it to the end of the array, the end of the queue, and when you remove, you're removing it from the beginning, right? So you're always removing things uh, in the order in which you add it into the queue. In Java, if you want to use a queue, use something called array queue. Sorry, array deck. Um, okay. So we're going to use this like a queue. And to use it like a queue, you do deck dot add. You give an element, and then queue dot remove, which returns and removes an element in the queue. And when you add, it adds to the end. And when you say remove, it removes from the beginning. So we need a queue because, right, we're looping through the nodes in the order in which we visit them, right? So that would be, I guess, in that case, that would be like breadth first search, right? Where we're removing them in the order in which we're adding them. Just like with flood fill, what we had to do with flood fill is we need to mark a node as having been like visited or not. Actually, a more proper term is like whether it has been queued or not in this case. And it's going to be of length n. So queued of I denotes whether node I has been queued or not. Okay. Yep. So to initialize, so yeah, we're going to need these two data structures to implement this breadth first search thing. And in this case, I know I'm using it interchangeably, even though they're two different algorithms. In this case, I am implementing breadth first search, not depth first. So I'm going to do q.add start, right? Because I want to start from the start node. So for this queue, I'll be queuing up nodes in the order of visitation. Okay. And any node that I've ever queued, you want to mark it as queued as well. So let's do that in the array. Okay, so how many times do we need to loop through this queue? Well, right now there's one element, but it's certainly possible that as we visit one element, we would be queuing up more of its nodes, right? Right. In this case, right, if we're visiting the top node, that we're queuing up 3 more nodes into the queue, right? So we should be looping as long as there are elements in the queue. And we want to count how many times we've looped, because that's also like how many nodes are actually reachable from that start node, right? So I'm going to say remove here, so that removes the beginning element in the queue. And then loop through all nodes that are reachable from this node here. And add them to the queue if they have not been added. Okay, so let's loop through each node. So how do we know if a node is reachable from that node? Well, we look at the graph, right? So we have to loop through that particular row of the graph. So in particular, we want to look at But so to see whether node can reach I, right, you check whether this is true, right? So if the loop through that entire row, which is okay. Right, so if this is true and node I has not been queued yet, then well, add it to the queue. And also mark it as queued. So every node that we visit, so like every time we iterate here, we visit the next node in the queue, right? So we do that. Just one little thing that I'm missing here is every time we visit, we increase our count. So count plus plus here. Yeah, and then at the end we do return counts. This is one of the harder algorithms, and it is one of those algorithms that I recommend you almost memorize, not line for line for sure, but conceptually, and you should be able to whip this out um, relatively quickly to do well in the contest.
Can you explain the queue algorithm again?
Right. So let me go back to the drawing board. So I'm going to mark any node that's red as queued, okay, and then any node that's yellow as visited, okay. Ah, terrible color. All right, so what I do at first to initialize the queue and queued is I put my starting node, which is at the top, into the queue. All right, so this is like before we even loop, okay? And then next, we keep looping while queue size is greater than 0, right? So I remove it from the queue and basically mark it as having been visited. And then I loop through all of the nodes and see like which one is actually reachable from that node, right? Which in this case would be these 3 nodes, okay? Yep. So when I add it to the queue, I also mark it as it has been queued. So that way, like I'm guaranteed to queue each node no more than once, and I have to do that. Otherwise, there will be infinite. I'll get an infinite loop. Okay, so since the queue, I am looping through the nodes in the order that I added them into the queue. So which node would I be visiting next? So I added these nodes boom, 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 left to right. So I guess like I'll be visiting the left one next, right? So I'm gonna go here. All right, and with this node, I like to do the same thing, right? So mark it as visited, right? So there's 2 nodes I've visited, and then loop through all nodes and see like which one is reachable from it. In this case, there's these 3 nodes reachable. from it, right? So I queue these up as well, and keep in mind that it is actually a queue, right? So again, we visit these nodes that's marked in red in the order in which we added to the queue. So the next node that we visit is actually going to be this guy. Okay, so we visit that, mark as visited, and again, loop through the neighbors that's loop through the nodes that's reachable from that node. And in this case, it would be here and here. Now, we don't actually add this node again, right? We don't want to double count this guy because it's already been queued. And the way we prevent that is that Boolean array. So the Boolean array where it marked any node that has been queued as well as queued of I being true, right? For any node I. So we're guaranteed to not put a node into the queue more than once. Okay, and then we visit this guy, and we loop through all the nodes that's reachable from it, right? Here, here, and here. So we only need to put this last one into the queue. Okay, and then if we continue looping, it goes that. Yep. Questions on this?
Wait, then how do you count like the maximum number of cows that each?
Oh, before I do that, let's talk about how efficient this algorithm is. So, uh, so in this case, what we just did is we did breadth first search. Okay. So the runtime, what is the runtime of breadth first search? We would at most visit each node once and each edge once. Because like for each node, right, we have to loop through the entire row in that 2D graph array to see like what are these edges. So in this case, it's O of n squared because like it's an n by n array, and we could be looping through each row, right? Plus, you also visit each node at most once, plus n, so that's still equal to big O of n squared. Okay, but it's not too bad in this case. This n is a pretty low number, 200. Okay, so now let's go back to the main. So, right, so Victoria is asking, like, how do we find the node that has the that's actually that can actually reach the largest number of nodes? Well, we just loop through every single node as potential starting point. Yeah, so we literally just do this for each starting node I. Do a count. Starting node I. And then our answer is going to be the maximum, right? Looks like there's a lot of inefficiency here, but it's efficient. So each call to the count function is n squared, and we loop n times to do that. So it's an n cube solution, which is still okay.
Is it because there's only 200 cows?
Right, 200 cubed is not too bad. That's 6 zeros, right? 200, so 200 is 2 zeros, so cube would be 6 zeros. And so it's 8 million. Not too bad.
Why do you add in the nodes that, like for, you have the starting node and then you go to each of the nodes that that starting node can reach.
Right.
But why do you add in the nodes that that the other node can reach, if that made sense?
Well, because I
Like, can
have
this,
to go through the entire tree here, right? Because if I start here, whoops, if I start here, I would know that, okay, these nodes are reachable, but then I have to decide like what nodes are reachable from those nodes as well, right? Because in the problem, they can relay the signal, right?
oh, right.
Yeah, so there's a recursive component to it, except I didn't do it recursively. Um, I did that using a queue. So since we did kind of bring up breadth first search and depth first search, the depth first search algorithm is basically exactly the same. It's just we visit the nodes in a slightly different order. So we visit that, and then uh, we queue up uh, these 3 nodes, and then um, we want to visit this node, right, and queue up on all the nodes that they can that node can visit, right? So it's these 2, right? And I guess we mark this as visited. Um, so with depth first search, what we do is we try to go down one path as much as we can, and then backtrack and then rinse and repeat. So like the next node that we'll be visiting in depth first search would be this guy here. Okay, and then we need to backtrack and then go here, right? And then we need to backtrack and backtrack again, right? Because well, actually, shoot, I miss this guy here. So I have to backtrack once and then go down there, right? So it's gonna be here, okay? And then I backtrack again, go down here, right? And then mark this as to be visited. Um, and then I go here, right? And then I backtrack, and then go here, right? And then I mark this as to be visited, right? And then I mark it. Uh, so there's that backtracking logic, and it seems really complex, but when we're actually implementing it, we don't implement the actual backtracking. Instead, we just use a slightly different data structure. Depth first search is like breadth
A stack?
first search, but with a stack instead of a queue. So a queue is sometimes called a FIFO data structure, as in first in, first out. But when you iterate through a queue, you iterate through the elements in the order in which you put them into the queue. Stack is the opposite. A stack is LIFO, last in, first out. Um, so what would you would do with depth first search is you would actually be putting it in a stack. And the way you put them in a stack is you would go from like right to left, I guess. So like when I mark these nodes, I'm putting them in the stack in this order from right to left. Why is that? Because it is last in, first out. Okay? So when I want to take something out of the stack, I take the last one that's been put in. So the last one that's been put in is here, right? And I would mark that as visited, right? And then I would put these two into the stack.
Can,
Yep.
do you have to use a stack for depth first search? Like, why can't you just use like a for loop or something?
You because as you visit, same reason we need a queue for breadth search. As you're visiting nodes, you are potentially you're potentially discovering more nodes to be visited, right? That needs to be marked as to be visited, right? So you need a
Well,
data structure to store that.
why can't you just make it like recursive, like for each node, visit all of its nodes?
You can do it that way as well. Recursion actually simulates a stack. Like when you have an infinite recursion, you get an error called stack overflow, and it's called a stack in every sense of this word. So function calls, the way it's implemented in in the compiler, is as a stack. So when you're making recursive calls, you're actually adding quote unquote elements or function calls into what's called a call stack. Yeah. So recursion actually simulates stacks. Uh, and I think I've said it before, but let me say this again. There's nothing you can do recursively that you can't do with a loop, and same thing vice versa. Um, so it really comes down to what you're more comfortable with. I like doing breadth first search, and in fact, I actually like doing flood fill this way as well because like flood fill, depth first search, and breadth first search, it's really the exact same algorithm. Uh, all I really need to change is uh, I use it as a stack. I use this array deck thing as a stack instead of a queue, and
Um,
I can actually make just 3 lines of changes here to turn it into depth first search. Yeah, go ahead.
does it um does it matter if you use depth first or breadth first search for flood fill?
No, it doesn't. But if you're doing that recursive thing that I showed you on Friday, it is one of those. Do you know which one it is?
Depth first?
It's depth first. Yep. So how do you turn it into DFS, into depth first search? So there's add and remove, right? With queues, with a stack, you can actually use the exact same data structure. Array deck supports both stack and queue operations. The verbs are a little bit different. Instead of add and remove, it's called push and pop. Okay, so to turn this algorithm into a depth first search algorithm, literally all you do is this line. So in q.add, you do. I guess you would call it stack. Otherwise, it will be a little bit confusing. Stack dot push start. Okay, and instead of doing remove here with DFS, you do stack dot pop, and then here you do push again. So you can use array deck still. It supports uh, uh, both stack and queue operations. And for this problem, it really doesn't matter which one you use. So
So what would be an example where it does matter?
Where it does matter would be you want to find the shortest path from one node to another. With depth first search, to give a more contrived example, with depth first search, it's not necessarily giving you. It could find you a path okay from one node to the next, but it doesn't necessarily give you the best path. So consider this is a start node and this is the destination node, okay? And we have two paths, or actually, let me write this like that. And the nodes and the edges are lined up like this. And let's assume that all edges point downwards, okay? So the shortest path from the green node to the destination node at the bottom would obviously be the right path, right? You go from here to here, and then here to here, right? But with depth first search, right, you go as deep as possible with one path, right? So you would be visiting this guy first, and then this guy, and this guy, and this guy, and this guy. So I reached that, but except that that's not exactly the shortest path, right? So with breadth first search, what you would do instead is you queue up these two nodes, right? And you mark this as visited, right? And then you go here, mark that as visited, and then you queue up this guy, right? But then we're visiting them in the order in which we're queuing. So the next node that we visit is actually this guy here, and then we mark that as queued, right? And then we visit that guy and queue that, but then the next one we actually visit is this, okay? So if for every node that we visit, we keep a reference as like where we visit, which node we visited from. So we have like a back reference, sort of, okay? And so we know that, okay, I got to this node from the start node, right? So I have a back reference like this, and then this node I have a back reference like that. Then I can actually reconstruct the path. Just reverse it, but we can just reconstruct the path, the shortest path from the start node to the destination node. Yeah. So for that, you do want breadth first search. Okay. I didn't expect this to take the entire class, but I guess we're just about out of time. Any other questions on this? All right. I was going to assign a slightly different graph search problem to you guys that has a twist on this, but I think this might be a lot of you guys' first time for doing this kind of graph search thing. So I'm going to find a simpler problem to assign for homework. I haven't figured that out yet. So yeah, wait for me to find a problem and look out for which problem to do in the homework in your email. So we got two more classes left, and I don't really have topics queued up for the next two classes. It's just going to be looking at problems that use the techniques that we've looked at for the past several weeks. But yeah. All right, so I will see y'all tomorrow.
Okay.
Okay.
Bye.
Bye.
Do you have time to answer a question about the cow art problem from Friday?
Yes. Okay. Yeah. Sure. Go ahead.
I ran the code in my own Eclipse, and then it said that I ran the code that was from the notes, and it said that there was a Stack Overflow issue
Oh.
on like.
Oh, that
Yeah.
might
In the sample input or in the more complex test cases?
Just in the flood recursive function,
But like
it says that,
which test case were you running it on? Just the sample input?
yeah, the sample
Okay.
input.
All right, then. All right, I messed up then. I should fix that. Let me pull that up. Actually, do you have the notes somewhere in your virtual machine so I can see it?
Uh, I made a copy of it, but I can try to pull it up.
Yeah.
Oh yeah, I found it.
Okay, okay, great. Uh, Good. So let me copy that and put it into my Eclipse. So car. Okay. Um, Let me look at the sample input. All right. I'm an idiot. Uh, I have not marked any one of these as visited. Yeah, I think I'm missing a line here.
Okay, so
Um, and it should be new R and new C.
okay.
No, it's still doing that. Okay. So another thing I should look at is and visited of new R and new C is false. So and not that. Index out of bounds. Region map. Okay. So yeah, there were some errors here, but okay. So not visited. Then go ahead and flood. This is wrong. You're right. I can do this. Do you need me for something? Sorry. All right, there we go. Right, I'm not sure why I'm getting the second part wrong, but this is the uh, updated version. So I'm making a couple of changes here, some typos, and also the big part here that I really should have caught was when I loop through the neighbors, I need to make sure that they haven't been visited as well. Uh,
Okay.
yep, sorry
Okay,
about that.
because I was trying to use this algorithm for like the harder problem yesterday and it didn't come out right. So
Right,
I was
okay.
just
Yep.
okay.
All right, sorry about that.
No, it's fine. All right.
Okay, thanks. See you tomorrow.
Thank you.
Yep.
See you tomorrow.